In this section, we're going to talk generally about inverse functions, and this is probably a subject that you have had before. It is a favorite topic of mine from the days of algebra. And so we'll just run through this as though it is a review, because I'm sure it is for you, and just talk about some of the techniques and ideas that you have discussed before. Well, the idea of inverse function is this, that if we take a function f of x and we can write it as y equals this expression, when we want to find the inverse, and I'm talking about generating the function which is the inverse of f, there are actually two techniques that are possible. One is to just replace x with y and y with x here. When we inverse, we just exchange the role of x and y. And so we can exchange roles right here, and then we can solve this for y. And that's the way I'm doing it here. The other way is to just take this form and solve this form for x and then exchange the x and y, but it really doesn't make any difference. Okay, here we go. I'm solving this for y, so I'll square on both sides. I have x squared is 2y minus 3. Adding 3 on both sides, I get x squared plus 3, and then divide by 2, and I get this. So I have y equals this expression. Now, the notation for this new relationship between x and y is that it's the inverse function of f, or it's f inverse of x. And the notation is f inverse of x like this. The little negative 1 here is not an exponent, it's the notation for inverse function. So the inverse function of x is this. Now, what you ought to notice about this is that functions and inverses have inverse operations involved in them. Look at what we started with here. We have 2 times x, we're subtracting 3, and we're square rooting. Well, the inverse operations then in the inverse function should be, let's see, the inverse of square rooting is squaring. The inverse of multiplying by 2 would be dividing by 2. The inverse of subtracting 3 would be adding 3. And we have all of those ideas down here. We have squaring, we have adding 3, we have dividing by 2. You see, so we're just exchanging operations. We're taking operations and we're writing inverse operations basically with the inverse function. Now, what's really intriguing about this, and there are a lot of things, but what's kind of neat is that all of the roles that are played by x and y are just reversed when you compare functions with their inverses. And that includes things like domain and range. The domain of this function, let's see, the acceptable replacements for x, the replacements for x that make sense. Let's see, we're taking square root, and if we're talking about real numbers, the real number system here that makes sense for us, then we want values of x that will cause the radicand to be positive or 0. So x has to take on values that are 1.5 or larger. So the domain then would be x is greater than or equal to 1.5, or in interval notation, it's the interval from 1.5 to infinity. And the range, let's see, the range means the y values that come out of these calculations. Turns out that when we take the square root of numbers, we always get positive numbers or 0. So y is greater than or equal to 0, or in interval notation 0 to infinity. Now the idea that when we go to the inverse function is that the roles of domain and range are simply reversed. That is, the domain of this inverse function will be the same as the range of the function itself. So the domain will be 0 to infinity. The range will be the same as the domain of the original function. So the range of the inverse is 1.5 to infinity. Interesting idea. Now, let's see how those ideas manifest themselves graphically. Well, if we were constructing the graph sort of by hand using a point plotting method, then we would take our function f and probably write it in the form of y equals the expression, and then we would generate points to plot. And we do that just by popping in values of x and figuring out values of y. Well, 3 values that could go in here are these 3. And I just chose values that turned out to have integer components here for both x and y. Now, when you perform the same kind of operation over here for the inverse function, you find out that you get exactly the same values but in reverse. All right, maybe I should say in inverse. That is, 3 points that happen to appear on this graph are the points 1, 2, 3, 6, 5, 14. Now notice here that the column of x values is the same as the column of y values over here. And the y's here are the same as the x's here. Another situation of this role of x's and y's being exchanged when we are talking about functions and their inverses. When we plot the points here, and look at the graphs, here's the graph of f, and here's the graph of f inverse. Now notice points like, for example, here's the point, let's see, 1, 2, 3, 4, 5, 6. This is the point 6, 3. And this is the point 3, 6. So if 6, 3 is on the graph of the function, then 3, 6 will be on the graph of its inverse, as we saw from the tables of values. We notice that there is a reflection idea, that a function in its inverse will appear to reflect in the y equals x line. This is the y equals x line. And there's really no mystery in that, in why that happens. There's a perfectly good reason why that reflection occurs. And let me illustrate that this way. If this is our coordinate plane, you know, on the x-axis the positive values lie out to the right and the negative values to the left, and on the y-axis the positive values are up and the negative values are down. Okay. What we'd like to do in this exchange process when we create or generate inverse functions is that we want to exchange positive x values for positive y values. You see, we're exchanging all the x's and y's. So positive x's become positive y's, negative x's become negative y's, and vice versa. So it's a complete exchange of those two. Now graphically, if we're going to exchange sort of positive for positives and negatives for negatives, you see, can we, for example, just take the x-axis and move it up here to the y-axis? Can we just twist it around? Well, that would exchange these positive x's and they would become positive y values. But in doing that, in twisting the whole coordinate plane around like this, these positive y values would become negative x values. You see, in that kind of rotation process. So what has to happen is this. We have to have a situation where we twist like this, you see. And in twisting like this for the graphs of the inverse functions, the positive x's become positive y's, and I'm twisting around these positive y values, twist around the back side, you see, you can think of it like that, and become positive x's, and the same idea with the y values. So no wonder we get that kind of reflection in the y-axis, in the y equals x line. Now, it's a reflection. It kind of looks like from the graphs that we have here that all of one graph will lie on one side of that y equals x line, and all of the other graph will lie on the other side. That's really not the case. The graph of one can certainly go through this imaginary line, and all that would happen is that we would have a twisting of that entire graph around this kind of rotation point, if you want to think of it like that. Okay, those are all characteristics that I'm sure you've seen before. The acid test to determine whether or not two functions are inverses of one another. And now we generated inverse functions a few minutes ago. And so we know that they are inverses of one another. But sometimes you're faced with a couple of functions and you're not sure they're inverses of one another. The acid test is to calculate the composite function. That is, compose the two both ways. That is, if one of them is designated f of x and the other is designated g of x, then to determine if f and g are inverse functions, then calculate f of g of x and calculate g of f of x. And the result of either of those should be x. For example, If f of x is this, it's a function we were talking about before, and g of x is that function we were talking about before, then f of g of x means, let's see, g of x is that expression, the fraction. F of the fraction means pop the fraction into this. So we have the square root of 2 times fraction minus 3. The 2's cancel, and we have x squared plus 3 minus 3. The 3's go out, and so we have the square root of x squared, which is x, because x is always positive here in this situation for f. And for the other composition, g of f of x is the square root idea. So the g of that square root business means to put that square root business in this position. So we have square root of business squared plus 3 over 2. Squaring the square root, that goes out. The 3's go out. The 2's cancel. How nice. We get x as expected. Suppose we want to generate the inverse of f of x equals x squared plus 3. We would replace f of x with y. We would swap the x and y. We would solve for y. Y squared is x minus 3, or y is plus or minus the square root of x minus 3. Now, does this represent y as a function of x? Not by our definition of function, because by our definition of function, a single value of x should generate exactly one value of y. And here that's not the case. If x is 4, we would have 4 minus 3, 1. The square root of 1 is 1, plus or minus 1. That one value of x, 4, is generating two values of y, plus or minus 1. And so we do not have y as a function of x. Now graphically we can see it even more clearly. The graph of this kind of looks like roughly like this. And so we're failing that vertical line test. Now, it was probably predictable that the original function would not give us an inverse that would indeed be a function if we simply look at its graph. The graph of the original function is something like this. Now, you see, we know that because we have this reflection characteristic in the y equals x line, that this graph is going to reflect in this line and turn out to be this, and it'll fail the vertical line test. And we can sort of backtrack the situation like this, that gee, if this inverse function has to pass a vertical line test, then let's reflect back to the original function. The original function then would need to pass a horizontal line test. And so we would know up front whether or not the original function would be able to pass that horizontal line test, and therefore whether or not the inverse would be a function. Now, in order for a function to pass a horizontal line test, what are the characteristics of its graph? Well, the graph would have to have characteristics like this. One of two things has to happen. Either the graph is continually increasing. You know, it might increase at different rates, but it's continually increasing, or it's continually decreasing. This kind of graph would have, you see, it passes a horizontal line test. Both of these do, and therefore the inverse would pass a vertical line test and therefore be a function. So continually increasing or decreasing is the characteristic that we're looking for. And it turns out that even with the functions that we were just talking about, even with the original f function, we could make some changes to that function just in terms of its domain and have a situation where we generate an inverse that is a function, like this. You see, suppose we take this graph and just lop off part of it so that this passes a horizontal line test. We can do that pretty easily by just taking this part off. Okay, now that translates into a limited domain. If we limit the domain here to x values that are greater than or equal to 0, then that should do it. And notice that the range is, let's see, y is 3 to infinity. So let's see what that looks like. Algebraically. Now, that translates down here to a situation where the domain is the same as the range here. You see, so the domain here is going to be x greater than or equal to 3. And the range will be y greater than or equal to 0. And if y is greater than or equal to 0, then it means that we have this situation. So we have that single half of the parabola up here and that single half of the sideways parabola over here. So by limiting the domain, we create a situation that we're after. Here are some characteristics of functions and their inverses. Let f be a function with domain of interval I. So f is defined on the interval I. If f has an inverse, now we're implying here that the inverse is a function. You know, that we generated an inverse relationship a moment ago involving an original function, and it turned out that that inverse relationship was not one of y as a function of x. So we're implying here, though, that this inverse is a function. All right, then if that's true, then if f is continuous on its domain, then f inverse is continuous on its domain. Now the domain here is I, but the domain here would be the range for f. At any rate, if f is increasing on its domain, then f inverse is also increasing on its domain. If f is decreasing on its domain, then f inverse is decreasing on its domain. And here's the kicker sort of for us as we move this idea into the idea of derivatives and integrals and so forth. If f is differentiable at c and f prime of c is not 0, then f inverse is differentiable at f of c. Let's calculate the derivative of two functions that are inverses of one another. I want to show you a relationship having to do with the slopes of those lines. If f of x is this function that we talked about before, I can divide 2 into both parts here and set it up for differentiation. F prime of x, then the derivative of this would be simply x, and this would go out. For g of x is the square root of 2x minus 3. G of x then is 2x minus 3 to the 1/2. G prime of x 1/2 times 2x minus 3 to the negative 1/2 times the derivative of this part, which is 2. And then the 2 times 1/2 goes out, and the negative 1/2 kicks this binomial into the denominator, and the 1/2 causes us to have a radical. So g prime of x is 1 over the square root of 2x minus 3. Now, let's consider a situation involving a point on one graph and its counterpart on the other graph. Now, if the point 3, 6 is on f, then it implies that the point 6, 3 is on g, and vice versa. All right, now, what about f prime at this point? Well, f prime of 3 means, let's see, replace the x with 3g, we would get 3. So f prime of 3 is 3. Now, what about the derivative at this point, the counterpart of the one on the f function? That is, what is g prime of 6? Well, g prime of 6, put a 6 in here, and we have 2 times 6, 12. 12 minus 3, 9. The square root of 9 is 3. This is 1/3. So g prime of 6 is 1/3. Notice the reciprocal relationship between these two. It turns out that inverse functions have slopes that are reciprocals. They have reciprocal slopes. Rather interesting characteristic. A notation to describe that is this, that g prime of x is 1 over f prime of g of x. Now, this thing about swapping the role of x and y and using the function notation in describing these things can be rather confusing. It's a little easier to think of the situation like this. If we think of a point A, B that's on, let's say, the g function, one of the functions or the other, and we're talking about g of A here, g prime of A, excuse me. g prime of a. So x is replaced with a, and this x is replaced with a. All right. Now, if we're talking about this point on the g function, then g of a would be b, you see. So this is nothing more than b. So g prime of a is 1 over f prime of b when the point ab is on the original function. I don't know if that cleared anything up or not, but that's the situation involving a more specific idea according to coordinates of points. And in a similar way, f prime, just reverse the f and the g here, and we get the same thing sort of in reverse.